Hello, and welcome to my talk. I will talk about electron beam melting. So we saw, I think most of the samples in the talks were based on laser, and now we will talk about electron beam melting. We done it with two goals. One was to produce fully auxetic structures via selective electron beam melting, and the other was to process pure copper and copper alloys. So we saw already a nice animation of laser beam melting, so let's take a look at electron beam melting. I will focus mainly on the differences. So it's a powder-based process, so we build also layer by layer, but we need to sinter our powder. That's because our electron beam consists of electrons, and electrons have electrical charge. So if we overcharge the powder particles, the forces will get stronger than, for example, the gravity force, and then we get powder blow up. So we need to have a stable powder bed before we start melting. This is a crucial step towards a stable process. So we are working at high temperatures that allow solid state sintering, so solid state diffusion. With this powder bed, we have it mechanically stable, so that increases not only the electrical conductivity of the powder bed, but also has a force between the powder particles. So even if they get charged up, they stick to the powder bed. The second difference is we use an electron beam. That means we deflect our electrons with magnetic coils. We are not using mirrors, while mirrors have a mass, and they need to be considered when deflecting the laser beam. So you are stick with some limitation on the deflection speed of the beam. We can use here magnetic coils, and therefore we can deflect the beam much faster. We are talking here about 1,000 meters per second and higher. That's what is possible. And that also can be used to heat up the whole surface of your powder bed. So we don't need extra heating if we want to have a high temperature process. So we use the electron beam for heating up the powder bed and also for melting. The second big difference to the laser is the absorption. The absorption of the laser, even if it gets absorbed, is within a few hundred nanometers. Here we talk about 10 to 20 microns. So it's within the size of the powder, which means you have a volumetric energy source instead of a surface energy source, which gives you more freedom. You don't rely anymore on heat conduction, but you can melt it instantly through the volumetric source. The penetration depth depends highly on the acceleration voltage of the electron beam. So even that is tunable. So if you have a machine, we are using right now 60 kV, you could go up to 150 kV. It's normal in welding, and you can even go to higher penetration depths and get a more volumetric source. So what did we do with that process? First, we focused on auxetic structures. So what are auxetic structures? Here we look at 2D structures. So on the left side, we have a normal honeycomb structure. The behavior of that structure is if you press it, it will get wider. If you simply flip the connection lines, you get auxetic structure by simply inverting that. And now if you press, it would get smaller. But this is due to folding. What we concentrate on are so-called chiral auxetic structures, which is twisting around a sender. So the structure on the right side. How do we get these structures? So no one sits down and draws it. So basically my professor did for the first structures, but we want to have a systemized way to get these structures. So what we do is we take normal structures, for example, simple cubic structures, and do a eigenmode analysis. Not every eigenmode of that structure is going to be auxetic, but they are very, very good candidates to be auxetic. So then, after this eigenmode analysis, we take these structures, put them into simulation software, and see if they behave auxetic when pressed, and if they do, we build them with electron beam melting. So what you see here is a fully 3D auxetic structure. That means if you press it, it will go down in all dimensions. This is not only for mechanical stress, this could be also due to thermal stresses. Is also interesting. So thinking of a structure, for example, with a Poisson ratio of 0 would mean that if you put it under stress, it doesn't change its width, which could be very, very interesting for applications. To prove that these are really auxetic structures, we build them, and then we simply do a compression test, and we measure the elongation while compression, and this structure, for example, has a Poisson ratio of minus 0.4. This is what it looks like when we do these tests. So on the left side, we see simply imaging following the structure, what happens, so, and measuring the elongation. In the middle, you see the same imaging doing correlation over the whole sample, and on the right side, this would be simulation. Of course, this is 10 times higher than what comes out in simulation. This is just to visualize. So the struts are not bending so far that they touch each other. It's just visualization. And here in the middle, you can see what happens with the structure and how it changes over the whole process. Then we have some collaboration where we try to do in situ compression testing. And also we used, together with Thales, we tried to use these structures as shock absorbers, because when you compress them, they get harder. It's also one of the interesting applications. Not only exclusive to auxetic structures, but very common to auxetic structures is also a phenomena known as band gaps. So auxetic structures also exhibit band gaps for phonons, so for acoustic waves. That also can be, in these band gaps, can be tuned due to a lattice size, thickness of the structure, and so on and so on. So this is also an interesting application. Now, let's come to the second part of my talk. And this is the process development for copper and copper-based alloys. So why copper? It's simple. We are using an electron beam, and our beam is not reflected by the copper. So we still have absorption values above 80% of our energy. So copper is basically an element that is very, very suitable for the electron beam melting. Plus, copper has a high thermal and electrical conductivity, what you can see here. This means it's good for the electron beam process because it has a high electrical conductivity, so the electrons go away. You don't have this powder blow up as for other alloys. And we can use the absorption of the electron beam. So what did we do with that? First, we try to find out what kind of copper do we want to use. Though we thought about some alloys, and we wanted to have a high thermal conductivity and a high electrical conductivity while still have good French properties, so have mechanical properties. And then we ended up with oxide dispersion strength copper, ODS copper. This is here in the graph on the far right side, the red area. And we thought it could be a good idea to use our process and manufacture parts with that alloy. Our experimental setup is basically building cubes. So everybody's saying you can build complex parts with additive manufacturing. We always start with cubes. It's the most easiest way. Our normal setup is we build cubes something around 15 times 15 millimeters with a layer thickness of 50 microns, and we do this simple hatching strategy where we scan the surface in a snake-like form with a line of sight of 100 microns, and each layer we rotate by 90 degrees so that the material transport to the melt is minimized to one end, so you change it every layer. The main difference of our beam is we can go up to 3 kilowatts. There is even more possible, but our beam width is higher than the normal laser beam width. So this would be 400 microns. For this copper and copper alloys, we used a process temperature of 380 to 530 Celsius. With titanium 6.4, we go up to 730, and with nickel-based alloys, we go over 1000 Celsius in this process. We work under low pressure with helium atmosphere, and this is the environment we need to have this low pressure because of the electron beam. Basically, it would be best to work in vacuum, but for process stabilization, it's better to have a low helium atmosphere, which is not interfering with the electron beam. So then we started, and we built it. We made it to build successful samples. So we had no powder blow up, and even though the process looks very unstable for those familiar with electron beam melting, it looked something like laser beam melting. So we always call it at our chair a moving volcano when you look at the laser. In electron beam melting, we are purely in the not in the keyhole regime, but only in diffusion. So we are welding through thermal diffusion. So we have normally we have no volcano, but with this we had it with this alloy. And if we take a closer look to the inner structure, we see what happens. So we have a strong demixing. So these dark areas are not binding faults or cracks or something. This is strong demixing. So we made pure copper and the oxide. So this alloy is not suitable for electron beam melting. I would also guess it's not suitable for laser beam melting. This was in the first time, but we kept to the copper because still copper is one element that is very good for this process. So now we use really pure copper. And first of all, we started to get where we get with the powder for pure copper, and what will happen to powder simply having pure copper. So on the right side, you can see the color after 3 months. On the left, after 3 years. Basically, if you order a pure copper batch from the same supplier 3 times, you will get 3 different colors. It's very hard to get good powder with really low oxygen levels, and you want them without oxygen, and you want them without phosphorus, because this lowers your thermal conductivity and your electrical conductivity. That means for weldability, normally someone would put in phosphorus to bind the oxides, but this is not good when you use it in additive manufacturing. You don't need that. So if you ever order powder, make sure that it's free of phosphorus and has a very, very little oxide level. Then we started and tried to build the first samples. So basically we did, as always, a process window, changing the beam power and scan speed and looking where are we porous, where are we heavy dense parts, where do we put too much energy in it and we have material transport, and so on and so on. And then what we do is we cut these samples, do eddy current measurements, and after that we do a laser flash analysis. So we measure the electrical and the thermal conductivity. And we also cut the samples and look at the microstructure. So the microstructure is pretty common to additive manufactured parts. Within the build direction, we get the microstructure columnar, and perpendicular to the build direction, which is the second cut, we get somewhat equiaxed microstructure. So basically, we have columnar growth. We managed to produce dense samples with a relative density of 99.5%. So we have no binding faults and everything. These are really, really dense samples. The porosity left here is due to powder production, so the porosity in the powder, but not due to the process. And we also reach 100% of the electrical conductivity measured by eddy current. So again, if you look at the volume energy, we saw that a few times defined today with various variables. This is also one definition of volume energy. We can look at the relative density. After a certain threshold, we reach these 99.5% relative density and above. And the same correlation holds for electrical and thermal conductivity. So if you have full dense samples with pure copper, you get the full electrical and thermal conductivity of pure copper. At the two right sides, we also see that some samples didn't get the full electrical and thermal conductivity, and those samples were with a high phosphorus content. So, as I said, it's common to put phosphorus into copper. We don't need it in additive manufacturing, so when ordering, not to waste time and money, don't use it. We can also look at the correlation between thermal conductivity and electrical conductivity, and we see that we have a very good correlation for the dense parts, which are the black dots on the upper right, and we have a bad correlation for parts with porosity. This is simple. When we measure the electrical conductivity and we have porosity in it, this porosity simply doesn't conduct, and since we measure it with eddy current, it depends on how the porosity is orientated to your measurement. So that's why we get this lower curve. But anyways, I'm guessing we always want to go to dense parts on the upper right. We also did some mechanical testing with the specimen. So again, build direction, perpendicular to the build direction, 45 degrees. These are normal tensile samples. What we did here, typical tests, and the good news is we get at the surface where it fractured, we get honeycombs, which are typical for pure copper parts. So these structures look like what you would expect it from copper manufactured by other processes. But we still have some orientation problems. So into the build direction, we have the highest strain. This could be due to the orientation of cracks, but we are not sure yet. So we didn't find any cracks, actually, not big ones, and in the new samples anyways, none. But this is one of the theories, because we have, again, this orientation, this columnar growth, and if there are cracks on between the grains, they would probably result in such a strain. But anyways, compared to the literature, still within the range. And we also have here tensile strengths and yield strength. Again, we have it's not isotropic. This is simply also due to the structure of copper. It's within the structure, within the material, it's also not isotropic, as you can see on the lower right. So the mechanical properties can be tuned again. So this is the same discussion as before. So do you want it, or do you want it, or do you not want it? So either you consider it while building, or you try to do some heat treatment or something else. With electron beam melting, we have also the possibility, we showed that with other alloys, mainly nickel-based alloys, that you can also tilt your structures. So controlling the process in that way that your temperature gradient while solidifying is not showing mainly directly upwards, but also in some tilted direction. So this gives you a freedom of some degrees. Could be also applied, but you need to consider it when building parts from it. So at the end, we could build complex geometries with pure copper. These are parts for the divertor. You can see two examples, I think, down there in the hall. What we have here is for cooling divertor, and what here was extremely hard is because we have this sintered powder bed, so the powder particles stick together. It was pretty hard to remove them from the pipes in there. We did some optimization with the part, and we did some optimization at the process so that we go at the minimum what we need in sintering while changing the geometry, and so we could remove the powder particles within this part, so it can be built. So thank you for your attention, and I'm open for questions.
With the auxetic structures, fascinating properties, we haven't been able to explore a lot of those. Is there an application that stands out in your mind
For copper?
the first place that we go to develop something that really makes the best use of the auxetic structure?
How do you mean the best use of the oxide structure? So auxetic. Auxetic. Yeah. Oh, yeah. Satellites. Let's shoot it into space. It's light. It's getting harder if you push it, and you can tune the Poisson ratio. So there are the applications, in my opinion. One second application that we also worked on is, and still work on, is in the energy sector. So you can use it as an absorber for sunlight. It gets under heat stress. So cloud comes, cools down, cloud goes away, heats up, and you can minimize the stress by simply changing the structure. Right now they're using normal structures, and if you use an auxetic structure, you minimize the stress on the whole structure, and you get the lifetime, which simply gets longer. So this is also one application that we work on right now. But yeah, so anywhere where you want this Poisson ratio below 0.
Thank you.
What cell size are the structures that you have?
Right now, as I said, our beam is about 400 microns. So this is the electron beam problem that we have right now, so we don't have better beams. We can build even smaller with the newest generation of Arca machines with these Q10 and Q10T, go down to 100 microns, but that's about it. So, but if you build 100 microns, there is a missing powder particle or something, or stick the powder particle. So that's limit.
I've got a few questions. I think I might catch up with you later on. So I was on the EBM here. One of the issues we have is your strut thickness, beam size. So you compare the tensile properties, bulk one, tensile bars. The mechanical properties you're going to get there is different to what you would actually get on the actual lattice structure. How did you compare that? Because the mechanical test that you showed.
Oh.
Different.
We didn't look at the mechanical properties of the structures in this talk. These structures, and so there is the weakest link will break first in these structures, but it's not going to be catastrophic. I have no graph here. It's going to go stepwise. So if you design your structure right, you will first lose one. If you push it like this, you will first lose one row, then the second, then afterwards. So you get a stepwise failure of your structure.
Okay. And lastly was the sintered powder. You said you reduced the sintering when you preheat.
Yeah, we go to the minimum.
So powder removal, is that what you did? Did you smoke?
That's the fun part about copper. So every other alloy smokes, basically, if you do it wrong. Copper is very immune to smoke because of its very high thermal conductivity. So you can do smoke, but it's not comparable to what you use with titanium 6.4 or something. So it will just move around the beam just a little bit, and that's it. So as I said, it's good to our process. So this is something that fits to the electron beam process very well.